Good evening everyone, good evening. I welcome you all again to your Vedantu Enlite channel. I hope all of you are doing great, having a good time. So people, quickly, let me know in the chats if I'm perfectly audible and visible to everyone. Let me quickly know in the chats if I'm perfectly audible and visible to everyone. Yes? Let me quickly know in the chats if I'm perfectly audible. Hi Yuvashri, hello MK, hi Arya. Hello Mukaddas, hello Berlin. Hi Ankita. Welcome back everyone. Just let me know quickly in the chats if I'm audible and visible to every one of you first. Yes, Sheikh, I'll be doing that after the session. Surely I'll be doing that. Hello Amulya. Hi Kurikula. Hi Lalit. Hi Jane. Hello GMK. Welcome back guys. Just give me a second, we'll be starting, right? Just give me a second. Okay. Hello Surendra. So I welcome you all again back to your Vedantu Enlite channel, right? We are meeting I think after 3-4 days, as you know I was not keeping well, right? Yes, we'll be starting the marathon sessions as well, no issues. Just wait for it. So people, in this tonight's session, we are going to cover the chemical equilibrium chapter, right? So I've come up with the set of problems which is going to cover your whole chemical equilibrium chapter from the start, right? So before solving every question, I'll be giving you the concept of solving the question. Then I'll show you exactly how to solve the questions in lesser time as well, right? So before starting this particular session, the ones who have just joined in, the ones who are new to the channel, let me quickly introduce myself. So people, my name is Wassim Sir. I'm your chemistry master teacher writer on this Vedantu Enlite channel, right? Yes. And the ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this Vedantu Enlite channel, right? So do like the video, share the video with your friends, and do subscribe to the channel as well. Right, people? Perfect. So let's get going. Let's get started. Just quickly, let me know if you all are super duper excited about this particular session as well. Yeah? Let me quickly know, my dear people, if you all are super duper excited about this particular session as well. Let me know quickly in the chats. Let me know quickly in the chats. Yes? Perfect, guys. So let's get going then. Let's get started with the first question, which is very simple, right? Based on one simple equation. So as per this particular question is concerned, it's a very simple and basic, guys, my people, right? It's very simple and basic. It is just, I want to show you one simple relation over here, right? Adnan, salt hydrolysis and solubility equations will be doing tomorrow. Tonight it's going to be for chemical one, and tomorrow it's going to be for ionic equilibrium, right? The thumbnail is already out for the ionic equilibrium questions as well. So tonight it's going to be only the chemical part, right? KP, KC calculation and so on. Alright people, so first thing, I'm sure you guys know one important relation, that is Kp is equal to Kc RT raised to the power delta N. This is a common relation which every one of you would be knowing, right? So first of all, if I talk about the first question, we need to write the Kp in terms of Kc for the reaction number 1, right? So let me quickly show you how to calculate delta Ng for the reaction, right? Delta Ng is always equal to number of moles of gaseous products minus number of moles of gaseous reactants. This is something which I would want you guys to know first of all, right? Delta Ng, number of moles of gaseous products minus number of moles of gaseous reactants. Now for the first reaction, if I want to calculate delta Ng, it's going to be equal to number of moles of gaseous products. See, this is in gaseous state and we have got its 2 moles. So number of moles of gaseous products in the first reaction is 2. Minus number of moles of gaseous reactants is going to be 1 plus 1, that comes out to be 2. So delta Ng value is 0. If delta Ng comes out to be 0, I'll write Kp in terms of Kc. I'll write Kp is equal to Kc RT raised to the power 0, and anything raised to the power 0 is 1. So for the first reaction, your Kp is equal to Kc, right? So for the first reaction, your Kp is equal to Kc. If you look at the second reaction, my dear people, let's calculate the delta Ng first of all. Delta Ng is nothing, it's number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactant, that's 1, so delta Ng is 1. So you can write Kp in terms of Kc like this. Kp is equal to Kc, RT raised by delta Ng, that's 1. So this is the relation between Kp and Kc. Yeah, simple. Similarly, if you look at the third reaction, my dear people, calculate delta Ng for the third reaction. So delta Ng for the third reaction is simply going to be number of moles of gaseous products, which is 2, minus number of moles of gaseous reactants, which is 1 plus 3, that comes out to be 4. So the value comes out to be minus 2. Since you have calculated delta Ng, so you can write Kp. So Kp is going to be equal to Kc, it's going to be RT, and it's going to be raised by delta N, which is minus 2, right? And at the end, if you look at the last reaction, my dear people, which is the fourth one, let's calculate delta Ng for this particular reaction as well. Delta Ng for this particular reaction is going to be equal to number of moles of gaseous product. This is in solid form, nothing to do with this one. Solid form, nothing to do with this one. So there's only one gaseous form, carbon dioxide, and we have got its 1 mole, right? So delta Ng is 1. So for the last reaction, you can say Kp is equal to Kc, RT raised to the power 1. I'm sure you got to know exactly how to write Kp in terms of Kc for different types of reactions, right? Perfect. Let me quickly move on to one more simple question. Have a look. This is the reaction which is given to me, right? You need to get the value of Kp. You need to get the value of Kp for the reaction that's given to me. So the reaction that's given to me, I'll be first of all calculating delta Ng for that particular reaction that's given to me, right? And delta Ng for the reaction is equal to number of moles of gaseous products. This is in gaseous form, this is in gaseous form, so I have to consider this one as well as this one. Stoichiometric coefficient 2, stoichiometric coefficient is 1, 2 plus 1 comes out to be 3. So number of moles of gaseous products is 3, minus number of moles of gaseous reactant, that's 2. So 3 minus 2 comes out to be 1. So you calculate delta Ng for it, right? After getting the delta Ng value, my dear people, you can write Kp in terms of Kc. So Kp is equal to Kc. Then you'll be writing RT raised to the power delta Ng, that's 1. Well, as per the question, if you have a look at the question, Kc value is given to us as 3 into 10 raised to the power minus 6 liter per mole. R value you'll be using as 0.0821 atm liter per Kelvin per mole. Or just to make the calculation simple, instead of 0.0821, just write it as 1 by 12. And temperature of the reaction is given to us as 427 degrees centigrade, that means 700 Kelvin, right? Raised power 1. You just need to solve this equation, right? And get the value of Kp, right? That's going to be the final answer of the question. So Kp for this particular reaction will come out to be finally 1.72 into 10 raised power minus 4. Let me quickly know if it is clear to everyone, right? Let me quickly know. Sabarish, I'm not getting what you are saying. Just be more clear what you are saying. Well, I've taken a session on molecular orbital theory. You can check that, right? You can check that maybe what you are saying about bonding and anti-bonding molecular orbitals, that might get clear to you, right? You just search it up, molecular orbital theory by Wassim Sir. You will be get one lecture, one detailed lecture of 1.5 hours, right? So whatever your doubts will be, those will get resolved, right? Perfect. Let me quickly move on to one more question, guys. In which of the following Kp and Kc are not equal? So first thing, when can be Kp and Kc equal? See, if I write Kp is equal to Kc RT raised by delta Ng for a homogeneous gaseous phase reaction, you guys know it. Now people, first thing, when can be Kp equal to Kc? Kp can be only equal to Kc if delta Ng is equal to 0, right? Because anything raised power 0 is equal to 1, then only I'll say for the reaction Kp value is going to be equal to Kc value, right? Now first thing, I need to check in which of the following equilibrium Kp and Kc are not equal, right? I'll say if delta Ng for the reaction is non-zero, for that particular reaction Kp won't be equal to Kc, right? Kp won't be equal to Kc, right people? So just have a look on the last reaction, my dear people. For the last reaction, if you calculate delta Ng, it's going to be equal to number of moles of gaseous products, that's 2, minus number of moles of gaseous reactant, that's 1. The value comes out to be 1, right? This is in solid form, I've got nothing to do with this one. So for the last reaction, delta Ng value is non-zero. That means for the last reaction, Kp and Kc won't be equal, right? If you check all the other ones, in all the other cases, your delta Ng will be zero. That means Kp and Kc will be equal, right? Perfect. Clear, guys? Simple. Let me quickly know in the chats if it's clear. Absolutely, you're perfectly right. It's going to be D, right? Okay, moving on to one more. A very simple and basic question again, just the formula based. We are given with a reaction. This is the reaction that's given to me. First thing, I'll be writing Kc expression for this particular reaction. It's going to be equal to concentration of B at equilibrium raised by stoichiometric coefficient, that's 1. Concentration of C at equilibrium raised by stoichiometric coefficient, that's 1. Divided by concentration of A at equilibrium raised by stoichiometric coefficient, that's 2. Now people, concentration of A, B and C at equilibrium are given to us, right? Just put all these terms into this expression. That is going to give you the value of Kc from here, right? You just need to write the Kc expression. Write the Kc expression, all these terms, all these concentrations of A, B and C at equilibrium are given to us. Just put all these values into this expression, you'll be exactly getting the value of Kc, which you were supposed to calculate, right? And let me show you the final answer which you'll be getting over here. When you put all these values into this particular expression, you're just getting the Kc value exactly as 6. Absolutely, guys, you all are perfectly right. Yes, exactly. This is one more question, a very common question, a very simpler one, right? I've started with the simpler questions only, guys. These are very simple, basic, right? See, one reaction is given to us, its equilibrium constant is given to us. I need to calculate the equilibrium constant for this particular reaction. See, guys, the reaction that's given to us, that's N2 plus 3 times H2, that's an equilibrium with 2 times NH3, right? And equilibrium constant for this particular reaction is given to us as K, right? It's K. Perfect. Now what I'll be doing, I'll try to make this particular reaction out of the given reaction. This is our given reaction. I'll try to make this particular reaction out of the given reaction. So what I'll be doing exactly? I'll just multiply this reaction with 1 by 2. If I multiply this reaction with 1 by 2, it becomes half of N2 plus 3 by 2 times H2 in equilibrium with, it's going to be NH3, right? What I exactly did, I multiplied this particular reaction with 1 by 2, and you know, whenever a reaction will be at equilibrium, if you multiply that reaction by some number, that number goes to the power of equilibrium constant. Now I must say the new equilibrium constant for this reaction is going to be K raised power 1 by 2, right? Just have a look on this particular reaction, my dear people, and this particular reaction, right? Its equilibrium constant is K dash, that means this value is K dash, right? So you got to know K dash is equal to root of K, right? K dash is equal to root of K. So option C is the one which is going to be the correct answer of this particular question, right? Perfect, guys. Simple and basic, I'm sure. You guys are doing it on your own because we have discussed all this in detail. All right, one more similar sort of question. Can you just solve it in less than 30 seconds, guys? See, a reaction is given to us, that is N2 gas plus 3 times H2 gas. It's in equilibrium with 2 times NH3 gas. This is the reaction that's given to us, right? And its equilibrium constant K value is given to me as 49. Now I need to calculate the equilibrium constant for this particular reaction, right? So what I'll be again doing, I'll try to make this particular reaction out of the given reaction, right? So how am I going to make it? I'll just reverse it first of all, and when I reverse this reaction, it becomes 2 times NH3 in equilibrium with N2 gas plus 3 times H2 gas. And you guys know on reversing the reaction, equilibrium constant is inversed, so the new equilibrium constant becomes 1 by 49 first of all, right? Now people, multiply this reaction with 1 by 2. When you multiply this reaction with 1 by 2, you get something like this. NH3 gives half of N2 gas plus 3 divided by 2 times H2 gas. Since you have multiplied this particular reaction with 1 by 2, that 1 by 2 will go to the power of equilibrium constant. So it's going to be 1 by 49 raised to the power 1 by 2. The value comes out to be 1 by 7. So 1 by 7 is basically the equilibrium constant for the reaction which we were supposed to calculate. I'm sure this is again clear to everyone, right? Perfect, guys, perfectly done. I'm sure it's clear. All right, moving on to one more question. This is one more question. Let's have a look what the question says. Again, the very simple and basic question. Have a look. We are given with the reaction first of all, and the reaction is something like this. That's HI gas in equilibrium with H2 gas plus I2 gas. I'm assuming the degree of dissociation for this particular reaction is, the degree of dissociation for HI over here is alpha. This is something which I'm assuming. Starting with 2 moles of HI, the total number of moles of reactants and products at equilibrium. All right. See guys, at time t is equal to 0, initially as per the question, we have got 2 moles of HI. We have got 2 moles of HI in the container, right? At time t is equal to 0, initially we have got 2 moles of reactants in the container. So at time t is equal to 0, since the reaction has not started, so this is going to be 0, this is going to be 0. Now you guys know at equilibrium, if I ask you how many moles of reactant will be left, it's going to be A minus A alpha, right? A minus A alpha. Now we use the stoichiometry. Guys, just a second. Something is missing, yeah. This 2 is missing over here. It's 2 times HI. It's 2 times HI. This 2 is written here, right? 2 is written here. So basically, out of 2 moles of reactants, I'm assuming, out of A moles of reactant, I'm assuming A alpha moles got dissociated, so I'll be left with A minus A alpha. Now use the stoichiometry. 2 moles gives 1 mole of H2. 1 mole of HI gives 1 by 2 moles of H2. So A alpha moles gives 1 by 2 into A alpha. That means A alpha by 2. So these are the moles of H2 which you will find in the container at equilibrium, right? Similarly guys, 2 moles of HI gives 1 mole of H2. So 1 mole of HI gives 1 by 2 moles of H2. So A alpha moles are going to give us A alpha divided by 2 moles of I2 at equilibrium, right? So if I ask you how many total moles will be there in the container at equilibrium, you will say the total moles present in the container at equilibrium is going to be A minus A alpha, this plus A alpha by 2 plus A alpha divided by 2, right? Simple. So people, A alpha by 2 plus A alpha by 2 comes out to be A alpha, and that gets cancelled with this, right? So the total moles present at equilibrium is equal to A. And what was the value of A exactly? A value was exactly 2. So you got to know exactly the total moles present in the container at equilibrium is simply going to be 2, right? Let me quickly know in the chats if it is super clear to everyone. So total moles present at the equilibrium is equal to 2, right? Perfect. Is it clear to everyone? I'm just using the basics of equilibrium and solving these basic questions. Look at this particular question, guys. It's again a very simple and basic question. Let's have a look what the question exactly is saying. As per the question is concerned, the reaction is given to us as A gas plus B gas. It's in equilibrium with 2 times C gas, right? 2 moles of A, 1 mole of B and 1 mole of C are placed in a 10-liter vessel and allowed to reach equilibrium, right? So at time t is equal to 0, my dear people, we are starting with 2 moles of A, we are starting with 1 mole of B, and we are starting with 1 mole of C at time t is equal to 0 initially, right? Now at equilibrium, I'm assuming out of 2 moles of A, there are some X moles of A which have reacted with B. So I will be left with 2 minus X moles of A at equilibrium, right? I'm assuming out of 2 moles of A, there are some X moles of A which are reacting with B, right? Now, if 1 mole of A reacts with 1 mole of B, that means X moles of A would have reacted with X moles of B. And I have taken some 1 mole, out of 1 mole X moles are reacting, so I'll be left with 1 minus X moles of B at equilibrium, right? Now already in the container there was 1 mole of C, right? Now 1 mole gives 2 moles, so from X moles you'll be getting another 2 X moles of C. So these are the total moles of C present in the container at equilibrium, right? Now people, if I divide all these terms with the volume of the container in liters, that means I'm converting these moles at equilibrium into concentration at equilibrium, right? I've divided all the moles of reactants and products by the total volume of the vessel, right, in liters. So this is something which I'll be calling as concentration of A at equilibrium. This is something now which I'm calling as the concentration of B at equilibrium. And this is what I'll be calling as concentration of C at equilibrium, right? Now we will have a look exactly. As per the question, if the final concentration of C is 0.2 molar, what do we mean by the final concentration of C? Final concentration of C means concentration of C at equilibrium, right? Because once equilibrium is established in the reaction, then there won't be any change in the concentration of reactants and products. The concentration of reactants and products attains a fixed value once equilibrium is established in the reaction. right? So once equilibrium is established, there'll be no change in the concentration of reactants and products. So it's mentioned that if the final concentration of C is 0.2 molar, that means the concentration of C at equilibrium is equal to 0.2 molar, right? Yes. Now what is the concentration of C at equilibrium, my dear people? Just have a look. It's 1 plus 2x by 10. It's simply 1 plus 2x divided by 10. This value is equal to 0.2, which is 2 by 10. So 10 got cancelled. So x, when you solve over here, it comes out to be 0.5. You got the value of x, right? You got the value of x. Yeah? Now people, if you got the value of x, put the value of x into all these terminologies over here. So x is 0.5. So 2 minus 0.5 comes out to be 1.5. 1.5 divided by 10 will be 1.5 divided by 10 will be 0.15. So this is basically the concentration of A at equilibrium, right? Similarly, 1 minus x. 1 minus 0.5 means 0.5. 0.5 divided by 10 is 0.5 divided by 10 is 0.05. This is the concentration of B at equilibrium. And 1 plus 2x by 10. 1 plus 2x by 10 already we know that is equal to 0.2 molar. So you got the concentration of each reactant and product at equilibrium, right? Once you get the concentration of each reactant and product at equilibrium, my dear people, you'll be writing just the Kc expression over here. And Kc expression is nothing. It is just concentration of C at equilibrium raised power stoichiometric coefficient, that's 2, divided by concentration of A at equilibrium raised power stoichiometric coefficient, that's 1. Concentration of B at equilibrium raised power stoichiometric coefficient, that's 1, right? Now we will have a look. You have got all the concentrations of reactants and products at equilibrium, right? Put all these terms into this Kc expression. So I must say Kc is equal to concentration of C at equilibrium, that is 0.2, raised power stoichiometric coefficient, that's 2. Concentration of A at equilibrium, that's 0.15, raised power stoichiometric coefficient, that's 1. Concentration of B at equilibrium, that's 0.05, raised power stoichiometric coefficient, that's 1. Just solve it and get the value of Kc. That's something which you were supposed to calculate, right? Yes? Is it clear, my dear people? Isn't it simple and basic? And this is how you are going to approach to this sort of equation, which is very simple and basic at the same time, yeah? Let me move on to one more. So the final value, which you'll be getting over here, is 6 by 3, right? All right, people, have a look on this particular equation. Have a look on this particular equation. This is again the simpler one. You are given with a vessel which has got the volume of 1 liter. And that vessel contains 1 mole of SO3. And that 1 mole of SO3 is heated till equilibrium is established in the reaction. And at equilibrium, 0.6 moles of SO2 had formed. The value of Kc will be. Now, how you are going to solve this question? Have a look exactly how am I going to solve this. It's again a simpler one. I'll be first of all writing the reaction again. It's going to be 2 times SO3 gas. It's an equilibrium with 2 times SO2 gas plus O2 gas. This is the reaction which is given to us. Number 1. Number 2, at time t is equal to 0, how many moles of SO3 are we given with 1 mole? So this is going to be 0, this is going to be 0 because the reaction has not started yet. Now I'll assume at equilibrium, out of 1 mole of SO3, there are some x moles of SO3 which got converted into the product. So I'll be left with 1 minus x moles of SO3 at equilibrium, right? Have a look on the stoichiometry, my dear people. 2 moles gives 2 moles. So 1 mole gives 1 mole. So x moles are going to give me x moles. As simple as that. 2 moles gives me 1 mole of O2. So 1 mole of SO3 will give me 1 by 2 moles of O2. So x moles are going to give me 1 by 2 into x. That means x by 2 moles of O2 at equilibrium. I just got the moles of each reactant and product at equilibrium, right? After getting the moles of each reactant and product at equilibrium, just divide these moles by the total volume of the container, which is 1 liter. Divide this term with 1, this term with 1, this term with 1. So I'll say these are the respective concentrations of each reactants and products at equilibrium, right? Right, people? First of all, these are the moles of reactants and products at equilibrium. At the same time, these are the concentrations of reactants and products too at equilibrium, right? Now, in the question, 0.6 moles of SO2 had formed. So number of moles of SO2 at equilibrium is given to me, right? It's given to me as 0.6. And we know how many moles of SO2 have formed at equilibrium, that's x. So basically you got the value of x, that's 0.6. Once you get the value of x, 1 minus x, 1 minus 0.6 comes out to be 0.4, right? X value 0.6, x by 2 comes out to be 0.3. So these are the moles of reactants and products, and at the same time these are the concentrations of reactants and products at equilibrium too, because the volume of the vessel in which the concentration is, the volume of vessel in which the reaction is taking place, that's 1 liter, right? So you got the concentration of each reactant and product at equilibrium, so you will just write the Kc expression, and I'm sure you guys know how to write. It's going to be simply concentration of SO2 at equilibrium raised to the power stoichiometric coefficient, that's 2. Concentration of O2 at equilibrium raised power stoichiometric coefficient, that's 1, divided by concentration of SO3 at equilibrium raised power stoichiometric coefficient, that's 2. Now you already have all these values, my dear people, have a look. You already have all these values. Put all these values into this expression, get the exact value of Kc which you were supposed to calculate. As simple as that. Let me quickly know in the chats if it is super clear to everyone. Let me quickly know in the chats. Final answer is coming out to be 0.68, yeah? I'm sure you got to know how to tackle this sort of equation. Alright, this is one more question. Again, it's a very simple one, right? Provided you just know the basic concept involved in it. Have a look exactly what the question says. As per the question is concerned, my dear people, we are given with a reaction, and the reaction is nothing, it's N2 gas plus 3 times H2 gas plus 3 times H2 gas. It's in equilibrium with 2 times NH3 gas. This is the reaction that's given to us, right? Now people, you guys know at time t is equal to 0, there will be only a reactants in the container. And when the reaction starts, what's going to happen? I'll say number of moles of reactants in the container are going to decrease and number of moles of products in the container are going to increase. So can I say at equilibrium there will be few moles of N2 left in the container, there will be few moles of H2 left in the container, and there will be few moles of NH3 which would have got formed in the container. So at equilibrium, if I ask you how many gases will be there in the container, you'll clearly say there will be 3 gases, right? There will be 3 gases. At equilibrium, I must say there will be 3 gases present in the container. So if I ask you, what is going to be the total pressure of the mixture present at the equilibrium? You'll use the Dalton's law. The total pressure of the mixture at equilibrium is equal to the partial pressure, the sum of partial pressures of each. I'll write partial pressure of N2 at equilibrium plus partial pressure of H2 at equilibrium plus partial pressure of NH3 at equilibrium. Isn't it simple, my dear people? Isn't it very simple, right? Now, what is the total pressure of the system, of the mixture at equilibrium? It's given to me as 2.8 atm. What is the partial pressure of N2 at equilibrium? That's given to me as 0.8. Right? Partial pressure of H2 at equilibrium, 0.4. And over here, you'll be calculating the partial pressure of NH3 at equilibrium. And once you solve it, you'll be getting the partial pressure of NH3 at equilibrium as 1.6 atm, right? So you got the partial pressure of NH3 at equilibrium too, right? Now people, you just need to write the expression for Kp. That's all you need to do, right? So Kp expression, how you're going to write it? You'll just write it as partial pressure of NH3 at equilibrium raised to the power its stoichiometric coefficient, that's 2. Divided by partial pressure of N2 at equilibrium raised by its stoichiometric coefficient, that's 1. Partial pressure of H2 at equilibrium raised by its stoichiometric coefficient, that's 3, right? Now, if I ask you, what is the partial pressure of NH3 at equilibrium, my dear people? It's 1.6. So isn't it going to be 1.6 raised by 2 divided by partial pressure of N2 at equilibrium? How much that is? That is 0.8 raised by 1. Partial pressure of H2 at equilibrium, that is 0.4 raised by 3. Just solve it. As far as I remember, the value comes out to be 50 exactly, right? The value comes out to be 50. If I ask you what are the units, since the pressure is given in atm, the units are going to be atm raised by delta Ng. atm raised to the power delta Ng. What is delta Ng for the reaction? Number of moles of gaseous products, that's 2. Minus number of moles of gaseous reactants, that's 3 plus 1, 4. So 2 minus 4 comes out to be minus 2. So 50 atm raised by minus 2 is going to be the final answer, right? Yes, simple. Right, people? I'm sure it's clear to everyone. Yeah? Moving on to one more question, guys. This is one more question. This is something which I'm sure every one of you can solve. The question says the equilibrium constant of the reaction is given as 300. If the volume of the reaction flask is tripled, the equilibrium constant will be. What will happen to equilibrium constant when volume of the reaction flask is tripled? Nothing is going to happen to the equilibrium constant because that is independent of the volume of flask, right? That's independent of the volume of flask. It's going to remain 300 only, right? The equilibrium constant is not affected by changing the volume of the whole reaction flask. That's all. Simple and basic at the same time. This is one more question, guys. Again, a very simple question. The question says, at time t is equal to 0, initially, at time t is equal to 0, we are starting with 1 mole of acetic acid, 1 mole of ethyl alcohol, and 1 mole of water. And this is going to be 0 at time t is equal to 0, right? Exactly, Arya. Equilibrium constant is just temperature dependent. Yes. Okay. So at time t is equal to 0, we have got 1 mole of this, 1 mole of this, and 1 mole of water in the container. That means there are 0 moles of this ester in the container at time t is equal to 0, right? Okay. So before the reaction starts, there is water in the container, and 1 mole of water is there in the container, as per the equation. Now, as far as the equation is concerned, 20% of the acid is being esterified. See, in this particular reaction, ester is getting formed. So you can call this reaction as the esterification reaction as well. So as far as the equation is concerned, the equation is saying 20% of the acid is esterified. What does that mean? That means out of 1 mole of the acid, 20% of this 1 mole is reacting. That means out of 1 mole of this CH3COH, 20% of this CH3COH, 20% of this 1 mole of CH3COH is reacting. What is 20% of 1 mole? 20% of 1 mole means 0.2 moles. That means out of 1 mole of this acid, 0.2 moles are reacting. So I'll be left with 1 minus 0.2 moles of this acid at equilibrium, right? Now use the stoichiometry. 1 mole reacts with 1 mole, so 0.2 moles would have reacted with 0.2 moles of this alcohol, right? So I had 1, out of 1, 0.2 moles have reacted, so I'll be left with 1 minus 0.2 moles, right? Now, again use the stoichiometry. 1 mole gives 1 mole, so from 0.2 you'll be getting 0.2. Already there was 1 mole of water in the container. Now there'll be additional some 0.2 moles of water which would have got formed at equilibrium, right? Because 1 mole gives 1 mole, from 0.2 you get 0.2, that's all, right? So this value is coming out be, okay, let's not do that. See guys, I'm assuming the volume of the container in which the reaction takes place, that's V liters. I'm dividing all these terms by the volume of the vessel, that's V liters. So I can call this term as the concentration of CH3COH at equilibrium. I can call this term as the concentration of alcohol at equilibrium. I can call this term as the concentration of the ester at equilibrium. I can call this term as the concentration of H2O at equilibrium. Once you got the concentration of all these reactants and products, you can just write the Kc expression which you were supposed to write, right? That's going to be equal. Concentration of this ester at equilibrium, that's 0.2 divided by V, raised per stoichiometric coefficient 1. Concentration of water at equilibrium, that's 1.2 divided by V, raised per stoichiometric coefficient 1, divided by, it's going to be 0.8 divided by V raised per 1, and it's going to be again 0.8 divided by V raised per 1, right? So V everywhere gets cancelled. Just put the values and get the value of Kc which you were supposed to calculate. Let me quickly know in the charts if it is super clear to everyone. Let me quickly know in the charts if you can solve these sort of questions easily from now on. Right, people? So final answer of this particular question is 3/8. Okay, look at this particular question again. The question says the total pressure at equilibrium is 30 atm. All right. And the partial pressure of HNO3 at equilibrium is 2 atm. Calculate Kp for the reaction. See guys, how am I going to do it? First thing, I'll assume at time t is equal to 0. At time t is equal to 0. There'll be only the moles of reactant in the container. There'll be, at time t is equal to 0, since the reaction has not started, there will be only the moles of HNO3 in the container. So, at time t is equal to 0, whatever the pressure of the container will be, that's going to be only due to HNO3. Because at time t is equal to 0, there is only HNO3 in the container, nothing else. So, whatever pressure will be there in the container at time t is equal to 0, that's due to HNO3, and let me call that as P0, right? The contribution of NO2, 0, this is 0, this is 0, right? Now people, you are going to treat these pressures in the similar way as you used to treat the moles. You are going to treat these pressures in the similar way as you are going to treat these moles. I'll write it as P0 minus X. Now use the stoichiometry. 4 moles gives 4, 1 mole gives 1 mole, X moles gives X. 4 moles gives 2, 1 mole gives 2 by 4, that means 1 by 2. From X, you get X by 2. And in the similar way, this is going to be X by 4. That's it. So these are basically the partial pressures of each reactants and products at equilibrium, right? These are the partial pressures of reactants and products at equilibrium. That's all. Number 1. Number 2, have a look. As per the equation, the total pressure at equilibrium is given to us. Total pressure at equilibrium is given to us as how much? 30 atm, right? Can I say the total pressure at equilibrium is basically the sum of these partial pressures? The total pressure of the mixture at equilibrium will be the sum of the partial pressures, which is going to be exactly P0 minus X plus X plus X by 2 plus X by 4, and this value is nothing, that's just equal to 30, right? At the same time, in the equation, it's mentioned that the partial pressure of HNO3 at equilibrium is 2 atm, and the partial pressure of HNO3 at equilibrium, that's P0 minus X. So basically, this whole term, P0 minus X, is equal to 2 atm. That's something which is given, right? So instead of this P0 minus X over here, you'll be writing 2, right? 2. Perfect. And this 2, you'll be taking on that side. So on the right hand side, it just becomes 28. On the right hand side, it just becomes 28. Just take LCM of these three terms. It's going to be 4. This is going to be 4x. This is going to be 2x. This is going to be x, right? So you get the final value as 7x divided by 4 is equal to 28. From here, you will be getting the value of x, which comes out to be 16 atm, right? So you got the value of x. If you got the value of x, my dear people, as per the equation, the partial pressure of HNO3 at equilibrium, that's P naught minus x. Partial pressure of HNO3 at equilibrium, that's P naught minus x. That's given to me as 2 atm. Well, you can calculate P naught from here, which is going to be 2 plus x, 2 plus 16, the value comes out to be 18 atm. So you got the P naught value as well, right? If you got the P naught value, if you got the x value, you can get the exact values of the partial pressures of reactants and products. P naught minus x is something which is given to be as 2 atm, right? X value is nothing, that's 16. X by 2, 16 by 2, 8. 16 by 4, that's 4. So these are the ATMs. These are the partial pressures of reactants and products at equilibrium. Once you get the partial pressures of reactants and products at equilibrium, you can just write the Kp expression, which is going to be equal. Partial pressure of NO2 at equilibrium, that's 16. Raised power stoichiometric coefficient, that's 4. Partial pressure of water at equilibrium, that's 8. Raised power stoichiometric coefficient, that's 2. Partial pressure of O2 at equilibrium, that's 4. Raised power stoichiometric coefficient, that's 1. Divided by partial pressure of HNO3 at equilibrium, that's 2. Raised power stoichiometric coefficient, that's 4. Just solve it, get the value of Kp, that's all, right? That's all what you have to do. Is it clear, guys? Tell me fast in the chats. Yeah? Is it clear to everyone? Let me know fast. Let's try to solve one more question, guys. Let me see exactly how this sort of a question is to be solved. Have a look. Again, this is a very simple and basic question, provided you know the basics of it. Yeah? See, the question is something like this. AB3 gas is basically in equilibrium with AB2 gas plus half of B2 gas. This is the reaction that's given to us. If the initial pressure of AB3 is 900 torr, at time t is equal to 0, this is 900. So this is 0, this is 0. The total pressure at equilibrium is 1000 torr. Now we are going to treat these pressures in the similar way as we treat the moles. So this is going to be 900 minus x, right? This is going to be x. And this is just going to be x by 2, because 1 mole gives 1 by 2. From x you get x by 2. That's it, right? As per the equation, the total pressure at equilibrium is 1000 torr. Total pressure is basically the sum of these partial pressures. Total pressure is basically the sum of the partial pressures. So it's 900 minus x plus x by 2. This value is basically equal to 1000, right? So this x got cancelled. From here you get the value of x exactly as 200 torr, right? So x value you got as 200 torr. Perfect. If you got the x value, my dear people, 900 minus 200 comes out to be 700 torr. So this is basically the partial pressure of AB3 at equilibrium. X is 200. This is the partial pressure of AB2 at equilibrium. X by 2, 200 by 2, 100 torr. Partial pressure of B2 at equilibrium. So if you got the partial pressures of each reactants and products, you can easily write the expression for Kp, and Kp expression is nothing. It's partial pressure of AB2 at equilibrium, that's 200. Raised by its stoichiometric coefficient, that's 1, multiplied by partial pressure of B2, that's 100. Raised by stoichiometric coefficient, that's 1 by 2. And partial pressure of AB3, that's 700 at equilibrium. Solve it, get the answer, that's Kp, right? Let me quickly know in the chats if it is super clear to everyone fast. Let me quickly know, my dear people, if it is super duper clear to everyone. I want every one of you to let me know fast if it is clear to everyone. Yeah? Let me quickly know in the chats. Perfect, guys. Let's move on then. Let's move on. Look at one more question. This is one more question. The degree of dissociation of N2O4 is this. It's a similar sort of question, guys. It's a similar sort of question. You're going to solve it, right, on your own. This is something which I'm giving you as the homework. It is a similar sort of question, right? You just do the concept as at time t is equal to 0, reactant moles will be A, then 0, 0, right? This is A, this is going to be 0, right? Then this is going to be A minus A alpha, this is going to be A alpha, sorry, 2A alpha, because the stoichiometric coefficient is 2. Then you will calculate the total moles at equilibrium, mole fraction of each reactant and product at equilibrium, partial pressure of each reactant and product at equilibrium, right? And get the value of Kp at the end, right? I'm not going to solve this question, you are going to solve this on your own, right? So let me move on to one more set of questions. This is one more set of questions, guys. Have a look on this. The vapor density of N2O4 and NO2 mixture at equilibrium. So vapor density of the mixture at equilibrium is represented by small d, and small d value is nothing, that is 30, right? Calculate the percentage dissociation of N2O4 at the same temperature. All right. Let me calculate the capital D value first of all. That's what we call as theoretical vapor density. This is theoretical vapor density, this is experimental. Theoretical vapor density is nothing that's molar mass of reactant divided by 2. What is the molar mass of this N2O4? It's going to be 92 grams per mole divided by 2. The value comes out to be 46. Capital D value you got, right? Now people, I'm sure you must have studied one formula, that is calculation of degree of dissociation, right, through vapor density measurement. And the relation is something like this: capital D minus small d divided by small d multiplied by n minus 1. So capital D value, you know, that's 46. Small d is 30 divided by small d, that's 30. N minus 1. What's n? The number of moles of products which we get from 1 mole of reactant. From 1 mole of reactant, we are getting 2 moles of product. So n value is 2 minus 1. Solve it, get the value of alpha. Once you get the value of alpha, then you'll be calculating the percentage dissociation. Percentage dissociation is nothing, that's alpha multiplied by 100. So you'll be calculating alpha from here, just multiply that value with 100, get the final answer, that's all. Right? So final answer is coming out to be 53%. So 53% is the percentage dissociation which you were supposed to calculate, right? Okay, look at this particular equation as well. This is again the similar. If the percentage dissociation is 40, that means alpha is equal to 0.4, right? Alpha is equal to 0.4. Calculate the vapor density of the equilibrium mixture. See guys, alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. Well, alpha value is given to us as 0.4. Capital D is equal to molar mass of reactant divided by 2. What is the molar mass of PCl5? See, phosphorus is 31, I believe, right? Yeah. Chlorine means 35.5. Multiplied, there are 5 chlorines, 5, 5, 25, 5, 5, 25, 27, 5, 3, 15, right? Plus 31. This is 5, 7 plus 1, 8, 7, 3, 10. So this is 208 divided by 5, whole divided by 2. The value comes out to be 104.25, right? So capital D value is molar mass of reactant divided by 2, which comes out to be 104.25, something like that. Minus small d, you need to calculate, small d, n minus 1. What is n? 1 plus 1, 2. So from 1 mole of reactant, you are getting 2 moles of product. So this is 2 minus 1. Look at this particular equation, my dear people. From here, you'll be just calculating the value of small d. That's what you were supposed to calculate, small d value, right? And let me show you the final answer. That's something you were supposed to calculate, right? Vapor density of the equilibrium mixture, small d. That comes out to be 0.013. Again, simple and basic only. Alright, this is one more question, guys. Let's have a look exactly what the question says. We are given with the graph between capital D by D versus alpha, right? So first of all, how do we solve this? What the question says exactly. For the reaction, the curve between capital D by D versus alpha is shown below. Calculate the percent dissociation when the experimental vapor density becomes half of the theoretical vapor density. So we need to calculate the value of alpha. When the experimental vapor density becomes the half of theoretical vapor density. Well, I can guess the answer. It's going to be 0.5, right? Okay, see guys how this question is going to be solved. First of all, you know the relation, that's alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. This is something every one of you would be knowing now. Yeah. Now people, you can write alpha multiplied by n minus 1 is equal to capital D minus small d divided by small d, right? Or you can write it as capital D divided by small d minus 1, right? Or you can write it like this: capital D divided by small d, capital D divided by small d is equal. It's going to be 1 plus n minus 1 into alpha. You can write it like this as well. Now you have plotted capital D by small d along y-axis, so this is your y basically, right? Alpha along x-axis, so this is x, this whole term is m, and this becomes the intercept c. Y is equal to mx plus c. It's straight line, right? And like this. What about the slope of this curve? Slope of this curve is represented by m, that's equal to n minus 1. So basically it's n minus 1 that's given to me. So from here you can calculate n. N value will come out to be 3. So n you calculate as 3. Once you got the n value, you can just use the formula. And the formula, you know, alpha is equal to capital D minus small d divided by small d multiplied by n minus 1, right? Now what do I need to calculate? I basically need to calculate the value of what? For the reaction to the curve, there's calculate the percent dissociation. Alright, I'll be first of all calculating alpha, right? And in the question it's mentioned that calculate the alpha when the experimental vapor density becomes half of the theoretical vapor density. So I'll write capital D minus. Instead of small d, I'll write capital D divided by 2. Instead of small d, I'll be writing capital D divided by 2. And it's going to be n minus 1 as such. So d minus d by 2 is d by 2. So d by 2 gets cancelled out. So alpha value is going to be 1 divided by n minus 1. n minus 1 is equal to 2. So 1 divided by 2 is equal to 0.5. So you got the degree of dissociation alpha 0.5. And once you get the degree of dissociation, you can easily calculate the percentage dissociation. Just multiply this degree of dissociation with 100, the value comes out to be 50, right? So percentage dissociation is exactly coming out to be 50. That's the answer, right? This is something which you need to solve. This is something which you need to solve. The question is based on the Lee-Chatelier's principle. We are given with a reaction which is at equilibrium, right? Now people, this reaction is taking place in a closed container, right? It's taking place in a closed container. That means volume of the container is fixed. Volume of the container is fixed. And you are adding an inert gas at constant volume, right? Addition of inert gas at constant volume is happening. What is going to happen then? Addition of inert gas at constant volume is happening, right? And when, you guys must be knowing, when we add inert gas at constant volume, nothing happens to the equilibrium constant, right? There'll be no change. There'll be no change. Absolutely, you all are perfectly right. There'll be no change at all, right? As per Lee-Chatelier principle, there'll be no change in the concentration of species at equilibrium if an inert gas is added at constant volume, right? But if the inert gas was added at constant pressure, definitely change would have happened, right? Okay, look at this particular question. The equilibrium amount of carbon dioxide can be increased. How can we increase the concentration? How can we increase the amount of carbon dioxide? How can we increase the amount of carbon dioxide? Okay, I can look at the option D. If I increase the amount of carbon monoxide, equilibrium will try to decrease it. And how equilibrium will decrease it? It will make sure the reaction moves forward. And when the reaction moves forward, the amount of carbon dioxide will increase, right? So option D is the one. Right, people? Option D is the one. On adding more CO, right, equilibrium will try to decrease it by favoring the reaction in the forward direction. The equilibrium will shift it forward. That means more carbon dioxide will get formed. That's all. Option D. For the reaction, this is the reaction that's given to us. The amount of X3Y at equilibrium is affected by, well, the moles on both the sides is different. 3 plus 1, 4, 2, right? So on reactant side, you have got 4 moles. On product side, you have got 1 mole, right? So basically, if you change the pressure, since the moles are different on both the sides, if you change the pressure, equilibrium will shift. Definitely it's going to shift, right? And similarly, depending on whether the reaction is endothermic and exothermic, equilibrium will also shift on changing the temperature. So basically, equilibrium is affected by changing temperature as well as pressure, right? So option A must be the answer. Yes, option A is the answer, right? Yes, equilibrium constant gets affected when temperature is changed, right? And at the same time, since the moles on both the sides, on reactant and product side, are different, so definitely on changing the pressure, since the moles are different, equilibrium will be getting affected. So people, these were some short questions from the chapter Chemical Equilibrium. I'm sure you guys would have enjoyed it, right? And got a lot of new concepts, right? Or maybe revised the Chemical Equilibrium chapter. And if you have not enrolled into this particular batch, which is the NEET 2022 crash course batch, my dear people, which is the JEE crash course batch, right? You should get enrolled in this as soon as possible, because if you think your preparation is not up to the mark, you're not able to handle it, right? This is the best way to score good in your JEE Means examination, right, people? Because in this, your whole syllabus in physics, chemistry, biology is going to get completed, number one. Number two, no need to worry about the test series, that's included here, right? Test series will be providing you free of cost. Study material, best teachers of Vedantu will be training you in this particular crash course batch. Do get enrolled, you still have got some 2 months left, right? So in 2 months, I'm sure you guys can definitely shoot up your ranks in your JEE Means examination, right? And how do we get enrolled into this particular crash course batch, which includes every single thing? Let me quickly show that to you. This is the video which you guys are currently watching, right? Just drag it a little down, drag it a little down, click on show more. After clicking on show more, over here, if you want to go for JEE crash course, go for it. If you want to go for NEET crash course, you can do that as well. The choice is all yours. These are 2 different links, one for JEE, one for NEET. If you are JEE student, click on JEE link, right? And drag it a little down, click on buy course, put your number, email ID on which you get the OTP and everything, and eventually you will be getting enrolled into the batch. Or if you're the NEET aspirant, just click on the NEET link, right? Definitely it's going to be helpful for you. Trust me on that, right? Because your whole course is getting completed from the starting. No need to worry about the test series. Every single thing is getting completed. So do get enrolled as soon as possible. Otherwise, it's going to be late, right? And it's completely affordable. In just 2,700, you are getting both the crash courses. So with this, guys, I'm going to take a leave. I'll see you guys tomorrow at 6 p.m. Okay, tomorrow I'm not going to take the session at 9:30. I'll be taking the session at 6 p.m. tomorrow. And the session is going to be for the chapter Ionic Equilibrium. So with this, I'll take a leave here. I'll see you tomorrow at the same time, 6 p.m. Till then, you take care. Bye-bye. God bless you all and love you all, my people. Take care. Bye-bye.